In this video, we're going to have a look at the idea of discrete random variables. So first of all, what are discrete random variables? Well, as the name variable suggests, it means it's something that has a varying number of possible outcomes. So in this example, we'll have a look and we'll see that we can have outcomes of 0, 1, 2, or 3. So it's variable in terms of the outcomes you can get. And because there is a finite number of outcomes, we would term those discrete variables. And each of those outcomes has an associated probability, which means that they are random, so discrete random variables. So if we take a look at this example, we've got Jake taking 3 shots at a basketball hoop. The probability of him scoring on any one occasion is 0.6. What is the probability distribution? What are the discrete random variables for the hoops that he scores? So first of all, we denote, the notation that we use is a capital X. Very commonly, that's the letter that's used to denote a discrete random variable. And we should always start the question by defining that clearly. So here I want to say that, that X is the number of times that Jake scores. So he can obviously score 0 times, once, twice, or 3 times. That's the maximum. So it's discrete data. There is a finite number of times that he could score. As opposed to, let's say, an example where I said he keeps on shooting at the basketball hoop until he scores. Well, that wouldn't be discrete because potentially he'd go on forever before he ever scores the basketball hoop. Now what we're going to do is work out what the associated probabilities are for each of these X values. So the notation we use for this is what is the probability that X, uppercase X, is equal to lowercase x. So what's the probability that X is equal to 0? What's the probability that X is equal to 1? And so on. So let's try and work out what those probabilities would be. The probability of me scoring no hoops would mean basically missing on all 3 occasions. That would be 0.4 times 0.4 times 0.4, and that comes out as being 0.064. What about me scoring on 1 occasion? Well, that would basically be either scoring, missing, and then missing, or it could be miss, score, miss, or it could be miss, miss, score. So I've got 3 different combinations of when I could score the hoop. And for each one of those, it'll be 0.6 times 0.4 times 0.4, because I've got 2 misses and 1 score. So if I work that out, I'll get 0.288. For this one here, number 2, again, I've got 3 different combinations. Because I'm scoring twice, that means I'm missing on 1 occasion. And I could miss on the first or the second or the third shot. So there's 3 times when I could be missing. And for each one of those, it'll be 0.6 times 0.6 times 0.4. 2 scores, 1 miss. That gives me then 0.432. And then I've got scoring all 3 times. That will be 0.6 cubed. And so I get 0.216. So that's called the probability distribution. That is the distribution of all the probabilities for this particular event that's taking place. And what we sometimes might choose to do is present that graphically. Normally, actually, we do it as a vertical line graph. So normally we'd actually have just a single line going up here. But I can then quite easily see what the most likely outcomes are, and I can see the shape of the distribution from this. Okay, so we've got probability on that side, and then the value of X on the x-axis. Another useful thing to calculate is the expected number of scoring shots. So what that sort of translates to is it's the mean, basically, of this distribution. If I was to perform this action, let's say 100 times, 1,000 times, so I was shooting at the hoop 3 times, and then I did it a second time, shot 3 times, a third time, shot 3 times. Let's say I did that 100 times. Then on average, how many scoring shots would I expect to have achieved? And we calculate that in a very similar way to how you work out the mean from a frequency table, whereby basically I would do this multiplied by this, add this multiplied by this, add this multiplied by this, add this multiplied by this. So just like with the frequency tables where you do the data value and multiply by the frequency, we do exactly the same for working out the expected value. And if you think with working out the mean, you would then divide by the total frequency. Well, in this case, that would mean dividing by the total probabilities, and that's just going to be equal to 1. So I don't even need to do that. I just literally multiply these together, add them all up, and that will give me the expected outcome. So that's the calculation, and that's then equal to 1.8. And that seems, if you think about it, that seems realistic based on this data. I can see that the most likely outcome, the one with the highest probability, is scoring 2 hoops. And I'd expect the value, the mean, to be pulled a little bit in this direction because I've got more data down here that's going to be pulling it down. So for it to have a value of 1.8, that seems reasonable given the distribution that I see in front of me. Just like we have a formula for the expected value of x, or the mean, which is very similar to the formula that we have when it's statistics, we also have a formula for variance and standard deviation, which is very, very similar. And just like before, with the mean, the main difference is that you don't have to divide by n because you're just dividing by 1. It's exactly the same thing here. With our variance formula, you can see that you are just not dividing by the n value that you normally would be, but it's still x squared multiplied by the probability, or the frequencies, subtract the mean squared. And we have the 2 different forms for it, just like we've done with standard deviation or variance previously. So just to very, very quickly do it for this example, all we're doing is we're doing this times this, but we're actually doing x squared multiplied by the probability. So we're doing, instead of 0, 1, 2, 3, we're doing 0, 1, 4, and 9, and multiplying it by each of the probabilities. And then we're subtracting the mean squared. Well, we already worked out the mean as being 1.8, so we're subtracting that, and that gives us therefore that the variance is equal to 0.72. The standard deviation, remember, is just the variance square rooted. So we take the 0.72, square root it, and then we get the standard deviation of 0.849 to 3 significant figures. We've actually hinted at it already, another common thing that you need to be considering when you've got a discrete random variable is that the probabilities are going to add up to 1. The sum of the probabilities is always going to be equal to 1. So in that case, I can say, what's the value of p? So it's going to be 1 minus 0.5, 0.2, 0.1, i.e. 0.2. So just to summarize that, the sum of the probabilities is always going to be equal to 1, or if you want to write that using sigma notation, the sum of the probability of x equaling x is going to be equal to 1. We're going to have a look now at a situation where we might use this to identify a game being a fair game. So a spinner has 5 equal sides numbered 1 to 5. If the spinner stops on an even number, you get 3 points. If the spinner stops on an odd number, you lose 2 points. Is this a fair game? So what I'm talking about with a fair game is I'm talking about a game where if I was to play this game numerous times, let's say 1,000 times, then I would expect the number of points that I've gained to be the same as the number of points that I've lost, so that it would balance out at being 0. So how could we show that mathematically? Let's again define what x is. So x could represent the number of points that I receive, and I'll create a table to show this. So obviously, if it stops on an even number, I lose 2 points. So the number of points I receive is -2. If it stops on an even number, I get 3 points, so that's +3. And let's look at the probabilities associated. So an odd number is going to be 1, 2, 3 fifths, so 0.6. And for the even number, I've got a 2 or a 4, so 2 out of 5, or 0.4. So how can I mathematically show if this game is fair or not? As I said, I want to imagine a scenario where I've done this game 100 times. If it's fair, then the expected value of x, the mean, I would expect that to be equal to 0 if it was a fair game. Because basically my wins and my losses would have balanced each other out and I'd end up with 0. Okay, if the expected value came out as being positive, then that means I've actually won more often than I've lost. I've ended up gaining more points than I've ended up losing. If it was negative, as would be the case probably in most casinos, because the house needs to win, you'd have a scenario where generally over a long period of time, playing this game, a lot of times I'm losing as opposed to winning. But if this is fair, then I expect the expected outcome to be equal to 0. So let's work out the calculation. It would be this times this plus this times this. That is equal to 0, and therefore this is a fair game. And again, if we just look at the scenario here, yes, I'm getting more points if it lands on an even number than an odd number. Because the odd number is going to appear 3 times in every 5, then the ratio of odd to even is 3 to 2, and therefore it kind of balances out. Let's look at a slightly harder example that involves this idea of having a fair game. So it costs me $10 to play a game. In the game I spin a spinner, which could land on a black space or a white space. The probability that it's black is 0.2, the probability it's white is 0.8. If the spinner lands on a white space, I lose my money. If it lands on a black space, I receive K dollars. We know that the game is a fair game, so what must the value of K be for that to be true? So let's draw out a table, and I haven't actually done this. I should have defined what x is equal to first of all. So let's say x is the amount of money I receive. So if I lose the game, I've spent $10 and I didn't get anything back, so I'm minus 10 down. Whereas if I won, then I've spent my 10, so I'm minus 10, but then I've received K dollars back, so it's minus 10 plus K. And what's the probability of each of these things? Well, losing was basically getting a white, so that's 0.8. That's going to go down there, and then it was 0.2 was the probability of getting a black, which is when I won money. So I'm expecting this to be a fair game, which means the expected value of x must be equal to 0. So I'll make an equation from that. This multiplied by this plus this multiplied by this must be equal to 0. And if we go through the steps of expanding the brackets and then solving that equation, we end up getting that k is equal to 50. So I would have had to have received $50 in order for this to be a fair game. One other scenario that we'll quickly look at is having a probability distribution that's defined not by kind of a real life situation when I can work out the probabilities, but a formula is given to me that enables me to derive the probabilities. So here I can see this is my formula. Probability that t is equal to t is a tenth 4 minus t, where t is equal to 0, 1, 2, 3, 4. So I just substitute those values into here to derive the probabilities. And this is what I end up getting. So the first one, 4 take away 0 is 4, times a tenth gives me 4 tenths, and so on and so forth. From this I can then derive various probabilities. So this is a notation that you're going to see very, very commonly throughout this probability distribution topic. So what is the probability that the random variable t is equal to 3? So that's then equal to a tenth. What is the probability that the random variable t is less than 3? Well, because this is a discrete probability distribution, less than 3 is the same as saying less than or equal to 2, because there are no numbers between 3 and 2. So if I'm less than 3, I must basically be 2 down. So I'll add these probabilities together, and that gives me 9 tenths. Greater than or equal to 2, well, this time I am including the 2, so it's important to look at the inequality to see if I am or am not including the value. And so greater than or equal to 2, this, and this is going to give me 3 tenths.